Non-ideal solution means when the solution does not obey Raoult's law over the entire range of concentration. It is called non-ideal solution. So when we say non-ideal solution, it does not follow Raoult's law over the entire range of concentration. So at certain concentration it may follow, but not for all the concentration. Now this non-ideal solution will surely have delta H mixing not equal to 0 and also delta V mixing not equal to 0. So both will be the characteristics of non-ideal solution. So vapor pressure of such a solution either is higher or lower than the predicted vapor pressure from Raoult's law. So if it is higher, then it is called positive deviation. If it is lower, then it is called negative deviation. So generally when we take two components, say x1 and x2, we have P total is equal to P1 plus P2. Now if actual pressure P total actual is greater than P total as predicted by Raoult's law, according to Raoult's law, then it is positive deviation, and if actual vapor pressure is less than the vapor pressure predicted by Raoult's law, then it is negative deviation. Both are important, both will be studied. Negative deviation. Here in such situations, actually the interaction between component 1 and component 2, that is solute and solvent, is not exactly same as that of 1 and 1. The interaction within the solvent and interaction within the solute. So because of which the solutions deviate from ideal behavior. So as a consequence, what happens is that they generally form what is called as azeotropes. So azeotropes are formed. So we will see what is azeotrope and what are azeotropic solutions surely. So now let us study the behavior of a positively deviating solution and negatively deviating solution. So we will be listing the features of positively deviating solutions and here it is going to be negatively deviating solutions. So basically these all deviations occur due to the difference in the interaction between solvent-solvent, solute-solute and solvent-solute. So if all are uniform or all are of same energy, then it will form ideal solution. Now here we have non-ideal solutions. So here very simple, interaction between solvent or interaction between solute particles is much greater compared to the interaction between solute and solvent. So if the interaction between solute and solvent, that is 1 and 2, is much less compared to the interaction between the solvent and the solute among themselves, then it is going to be positively deviating solution. So similarly in negatively deviating solution, we have the interaction between solute and solvent, that is 1 and 2, much greater than the interaction between the solvent and the solute among themselves. So As a consequence, what happens in positively deviating solutions is that we have enthalpy of mixing greater than 0, and also delta V mixing will be greater than 0, and as a consequence what happens is the partial pressure of the system will be greater than Pi naught into Xi. Actually Pi naught into Xi is the prediction of Raoult's law. So observed vapor pressure will be much more than the vapor pressure of the solution or the system as predicted by Raoult's law. So these solutions which are positively deviating from Raoult's law will actually show azeotrope formation, and they will be minimum boiling azeotropes. Minimum boiling azeotropes. So what is the meaning of minimum boiling azeotropes? Very simple. Minimum boiling azeotropes boil at a certain fixed temperature when they are of a certain suitable concentration at a boiling point much lower than the boiling point of the both of the components. So best example here is actually solution of ethanol and water. Best example here is that of ethanol and acetone, and we have carbon disulfide CS2 and acetone. Even ethanol and water will work, ethanol and water, and even methanol and water. So basically what happens is water has a higher intermolecular force, that is hydrogen bonding, whereas methanol or ethanol has a lower intermolecular force. So what exactly happens is when we add methanol in water, the interaction between the water molecules is also disrupted, and the newly established hydrogen bonding will not be as powerful as that of the initial interaction between the solvent particles. So as a consequence, the solution deviates positively. Now the features of negatively deviating solutions: obviously delta H mix will be less than 0, and delta V mix will be also less than 0, and the actual vapor pressure of the system will be much less than the vapor pressure of the system as predicted by Raoult's law. So they form maximum boiling isotopes. Form maximum boiling isotopes. So that is an important feature here. So best example would be phenol and aniline. See, each of them have certain extent of hydrogen bonding, but when they both are mixed, the extent of hydrogen bonding becomes more. So interaction between solvent solute is much more powerful than the individual interactions of solute as well as the solvent. So another example is actually chloroform CHCl3 and acetone. This is also a very good example. And we have ether, diethyl ether, that is ET2O, and chloroform CHCl3. So like this, there are negatively deviating solutions in nature as well as there are positively deviating solutions in the nature. Next term which we want to learn is actually azeotrope. Azeotropes. So azeotropes are binary solutions that have same composition both in liquid and vapor phase. and boil at constant temperature, So this can occur at only specific composition. So there are two types of azeotropes, as we have already seen: minimum boiling azeotrope and maximum boiling azeotrope. So generally solutions which show large positive deviation from Rolle's law form minimum boiling azeotrope. So that is generally indicated by the graph, the positive deviation. This is for positive deviation, and the graph for this positive deviation is like, you have x1 equal to 0 here, x2 equal to 1, and x1 equal to 1 here, x2 equal to 0 here. Suppose this is p1 naught and p2 naught here. So in this way the graph for ideal solution would be like this. Now this solution is not ideal solution, it is showing a positive deviation, so it will have actually pressure like higher than the partial pressure predicted from Rolle's law. So in this way the solution showing a positive deviation at certain suitable concentration, say somewhere here, will form a azeotropic solution. Example for this is actually 95% ethanol solution with water. 95% ethanol solution with water, that is also called as rectified spirit, is a positively deviating azeotrope. So it's a positively deviating solution and it forms azeotrope at 95% ethanol solution. So in this way the solutions which positively deviate form minimum boiling azeotrope. Similarly we have solutions showing negative deviation. So for such case the graph will be something like this. Say x1 equal to 0 here, x2 equal to 1, x1 equal to 1, x2 equal to 0. So it will be, say, p1 naught here. So this has to be p2 naught here and p1 naught here. So similarly p2 naught here and p1 naught here. So in this way this is actually the pressure predicted by Rolle's law. Now because it is forming a negative deviation, the total vapor pressure will be much lower than that of the prediction by Rolle's law. Similarly here also, so this is considering that only a particular solvent is present. So this is actually the vapor pressure of solution. So here we can mark vapor pressure of solution, vapor pressure of solution. So example for this type of negatively deviating solution that forms azeotrope at a suitable concentration or composition is that the mixture of HNO3 and water. So 68% HNO3 solution, 68% HNO3 and 32% water forms a maximum boiling azeotrope. So basically the boiling point here increases from the boiling point of both of the species. So water generally boils at 373 Kelvin, but 68% nitric acid boils at 393 Kelvin. So in this way there are many other examples which can be taken as example for azeotropic mixtures. So with this we conclude our discussion on azeotropic solutions.